Okay, in today's session we're looking at something that's new, the set of complex numbers. So mathematicians had a little bit of an issue that they needed to solve. So things like when we had things like this, x squared equals minus 1, or x squared equals negative 9, for example. For us to find the solution to that, we normally look at the square root of it, so positive and negative square roots. And of course, in real terms, we can't actually do that because you can't have the same number multiplied by itself to give a negative number, so that's always going to be a positive answer. So mathematicians had to solve that. So the way they solved that was that they came around with complex numbers. So complex numbers have two parts to them. They have a real part and the other part is, let's get rid of that, spell that properly. They have a real part and an imaginary part. So that's how we get around that. So let's clear that. And so the definition then is that the imaginary part is use the symbol I. To represent it, and the whole key to it is that I squared equals negative 1. So when we have something like, for example, the square root of negative 9, let's take the square root of negative 9, we need to rewrite that as the square root of negative 1 times 9, and negative 1 by definition, whoops, don't want to clear all of it, just the last bit, by definition is I squared, and 9 of course is 9, and so we can square root 9 to get 3, square root I squared to get I. So hence solving the problem of not being able to take the square root of negative numbers. So we have a complex number. Now, our notation that we use for complex numbers is this. Z is the symbol that we use. Equals A plus BI, so it has two parts. Where A and B are real. And the real part, or the real component, or RE of Z, that's equal to A, and the imaginary component IM of Z is B. Okay, so we don't need the I part. If we're just looking at what is the imaginary component, we're just looking at the size of it. Okay, so for example, if we have Z equals 5 minus 4i, then the real part of Z there would be 5, and the imaginary part of Z is negative 4 on that one. Alright, equality of complex numbers. Okay, if if we've got two complex numbers and they are equal, then that means that the real parts and the imaginary parts have got to be the same. So if a plus bi is equal to c plus di, then a equals c and b equals d. Both of those conditions have to hold. So, for example, if, say, x plus 2 plus y take 4i equals 2x plus y plus xi, then we can solve for x and y. And we can solve for x and y in the following fashion, because we know that the real parts, x plus 2 and 2x plus y, have got to equal each other. And if we then rearrange that, then what we're going to get is, if I move this 2x across over there, we're going to get minus x plus 2 equals y. And the other thing we know is that the real component, the imaginary component, I should say, y minus 4 and x, they must equal each other as well. So we've got two equations here, 1 and 2, and we can do a little bit of substitution. So if we do that, substituting equation 2 into 1, and then we're going to put that in there instead of x. So when we do that, we get the negative of y minus 4 plus 2 equals y. And then we just need to do a bit of a rearrangement. So y would be equal to 3, and from that x would be negative 1 when we go and substitute back in. Okay, so that's when two things are equivalent to each other. Alright, next we'll have a look at multiplying by a constant. That's not too difficult, and it's just a math. So if z equals a plus bi, then kz equals ka plus kbi. Pretty simple. So the example then we've got is z equals negative 2 plus 3i, then 4z equals 4 times negative 2, negative 8, and 4 times 3, 12i. Alright, one last thing, adding and subtracting. Again, not too difficult here. All you need to do is remember that we have two complex numbers, z1 equals a plus bi, z2 equals c plus di. Then all we do is just add the real and imaginary components. So z1 plus z2 would be a plus c, the real components added together, and b plus di, the imaginary components added together. The subtraction, of course, we would just subtract our real and imaginary components. So it's going to be A minus C for the real part and for B minus D for the imaginary part. Okay, so let's have a look at a couple of examples. So here we've got Z1 equals 2 minus 3i, and Z2, that's negative 3 plus 4i. So if I'm going to do Z1 plus Z2, then I'm going to add my real components, so 2 plus negative 3. And add my imaginary components, negative 3 plus 4. So I get negative 1 plus I for that one. Pretty straightforward. Okay, so let's get rid of that example. Using the same two complex numbers, if I wanted to do, say, 3 times Z1, and from that I'm going to take 4 times Z2, then I just need to make sure I multiply first of all. So 3 times Z1, 3 to 6 minus 9i, and from that I'm going to take 4 times Z2, so 4 times negative 3 is negative 12, and 4 4s are 16i. Okay, and now subtract my real and my imaginary components. So 6 minus negative 12 is 18, minus 9 minus another 16 is minus 25. So minus 25i there for that one. Okay, so that's it. So that brings us up to set number 4. So you have set number 4 on your sheet, exercise 1D.